Okay, this is section 2.4, and it's about key features of graphs. Specifically, we'll be looking at turning points, asymptotes, and intersection points. Um, Kind of the big picture. Another thing that is kind of a key feature is growth rates. That relates to calculus, so we'll get to that later on. But um, all are kind of big, important key features. High points, low points, turning points. Concept, functions are used to model real-life phenomena, and their graphs are an important piece of visualizing that. Learning how to use your graphing. GDC is graphical display calculator. Anytime you see that, it means graphing calculator. To find axes, max mins, asymptotes, we're going to find those by hand, and points of intersection between graphs. We'll all do on a graphing calculator. So, turning points. Turning points. Functions are increasing as they go up from left to right and decreasing as they go down left to right. An important thing, do not call this increasing because it's going up as you go that way. We read left to right, we read graphs left to right. It's easy to make that mistake at first. Minimums and maximums, there's global versus local. Remember with local, this one has two local maximums where these two dots are. Local means it is the max within a given area around it. There's a local min down here. This graph is going to go forever downward, so it does not have an absolute minimum. Global maximum here. Any maximum is a local maximum. So even if it's global, it's also local. This one has a local min. It does not have a global min. Okay. I'm not just looking at what's the lowest minimum. It's is that the lowest point on the graph. Okay. Sketch this graph showing all the relevant points. So if it says sketch the graph, you get a graphing calculator. It's the first step. I'm going to look at it and go x cubed minus 3x minus 2. So I just start by typing it in here. All relevant points. So relevant points would be things like intersections or x-intercepts, maxes, mins. So I find those with analyze graph. Let's do the zeros first. Okay, that is right on there. One thing that's helpful with the TI Inspire, this little hand, oops, I'm clicking on the wrong side of the mouse. If you click on it, you can drag the point around so it's easier to see, so things aren't written on top of each other, because it will label them on top. That appears to be a maximum. Menu. Let's go find the minimum. Okay. So if I'm sketching this graph on my paper, things that they want to see, Points must be labeled, important points like x-intercepts. Depending on what they're asking for, points of intersection. Um, Useful one here would be a y-intercept. I did not get that off the graph. I just plugged in 0 for my two x's and I get 0 minus 3 times 0, which is 0 minus 2. So here I have a quick sketch of my graph that looks roughly like it with the maxes, mins, and all the x-intercepts labeled. That is plenty of detail for this, but you will not get points without all those things labeled. You'll get partial credit at best. Sometimes you'll use a graph to solve. If you don't label the points that you got to solve, they don't give you credit for the graph, for the work. You'll still get credit for the answer, but you just lost a point by not being thorough enough in your labeling. So yes, hey, without looking, I knew all the points they wanted. Okay, kind of points that they're looking for. Showing, okay, we got another one. Showing all relevant. Okay, so let's go back. Let's graph this one. To get back to a graph, I'll just hit tab. X squared plus 11x minus 6. Um, I have no idea what this point is. So I just need to find all my relevant points, my zeros. It appears like this is going to be 1, 0, and the other one's 3, 0, but I'm going to check. Okay, so there's a lot of stuff crowded into here. Right now I'm just moving these out of the way. And when I sketch my graph, I will draw them out. Now I need to find my maxes and mins. It shows a minimum. I can read that. Let's just get this graph out of the way. I probably should have just cleared my graph entirely, but so if I'm making my sketch, I'll start with my y-intercept, 0, negative 6. I've got a max here and a min here. Put that in here. They like three significant digits. And the whole number ones, it's fine not to hit, but you don't need to put 3.00. I'm just kind of drawing labels to the points so that they're readable. Okay, that's a basic graph and the style that IB would like to see it. Unfortunately, they probably won't ask you for one that's that easy. To clear the graph, hit the delete button 3 times and start again. Okay, now we're looking at asymptotes. An asymptote, we're going to look for horizontal and vertical asymptotes. If we're looking in the form like this, that's your horizontal asymptote. Your vertical is where does it equal 0? So where does essentially the denominator x minus 1 equal 0? So 1. Vertical asymptotes have equations x equals horizontal, or I think in pre-calc we often called them end behavior asymptotes. I wouldn't use this abbrevi abbreviation on an IB exam because I'm not positive if they'll know it. Is 2. If they give them in that form. Looking at something like this, again, I can slightly different graph, but almost the same thing. I can see my horizontal or end behavior asymptote is at y equals 2, and my vertical asymptote is at x equals 1, because that's the solution to x minus 1 equals 0. So we might be asked to write this with end behavior notation. And so limit, and they've got some sort of limit notation. If you use limit notation on the exam, they'll be happy. Limit as x approaches infinity. And this function is called f of x. You could write the 5 over x minus 1 plus 2 in there, but you can just use f of x if you want. Goes to 2. Limit as x approaches negative infinity. So these are my two end behavior, not of f of 2, of f of x, equals 2. Those are my two end behaviors in limit notation. Limit as x approaches my asymptote. The plus means coming from the right side or from the positive side of the graph. Is infinity. So this is how I can notate along an asymptote of f of x as I'm coming to f to 1. So my graph is going towards 1 from the negative side. The y coordinate, the value of the limit, is going towards negative infinity. Those are notations. If you use these limit notations, they'll accept other notations, but that's probably the most standard and the most used and the most useful for your future. And we will be doing limits in calculus, so they will like you showing that knowledge. So sketch this graph showing all relevant features. I'm sick of this x minus 1. We're going to do something different. So we're going to do a similar function, but half of x equals 1 over x minus 3 plus 4. So let's do x plus 3. So my vertical asymptote, I'm looking at x plus 3 equals 0. That's -3. My horizontal asymptote is at 4. I'm going to draw dashed lines in here on my asymptotes. This one I believe is going to be over here. My y-intercept would be 4 1/3. That's a key point. 0, 4 1/3 is 13/3. Gonna be that point. X-intercept. So I plug 0 in for f of x. I multiply both sides to solve this by x plus 3. So I'm doing this all by hand, mostly because I think it's a good exercise for you. So it gives me -4x minus 12 equals 1. -4x equals, I add 12, 13. X equals -13/4. So that's -3 1/4. My branches have to go through those parts. And yes, I absolutely could have used that. That's their one. They labeled the same type of things that I did. I like my slightly altered equations. They're not all the same vertical asymptote. Okay, quick theory of knowledge connection, and then we'll do intersection points. Functions and their corresponding visual representations via graphing are useful for a variety of reasons, but foremost for their ability to inform in regards to real-world data trends. Such graphs facilitate stock analysis, population predictions, legislation related to human migration, to name a few. It seems mathematics is describing something through, though something, though is mathematics a language? That's a question you can debate and think about. What elements must be presented for something to be considered a language? Does math share these? Or these elements? You can discuss this in theory of knowledge class. Intersection points. Consider this. Use a graphing calculator to determine the intersection points. So here's a graph where they've done it. Notice the graph. When you sketch the graph, you must label all intersection points. Potentially, it'd be useful to label x and y intercepts, but depends on the nature of the problem. Identify these intersection points. So we'll graph them both on the graphing calculator. Um, I have to look at the other one again because I can't remember it. X cubed minus 1/2 x plus. Looks like I only have one point of intersection. It's not actually showing on this graph. So first thing we're going to do is change our window. And I'm just going to, all I need to change is the Y max. Let's make it 20. That'll put it kind of in the middle. Menu, analyze graph, intersection. And I will drag it away so I can see it. So there is using the calculator. If you need to draw it, make sure you draw what you see. And yes, that's what we got. Um, you can do all kinds of things with these. So this portion of IB mathematics syllabus examines how to use a graphic display calculator and a mathematical computer that calculates is an expectation for the curriculum. Since most mathematics students are still taught how to handle problems with and without computers, consider the different means by which mathematicians deal with proofs, whether entirely pen and paper or using a computer. Generally, proof, unless you're going to do an exhaustive show every case, the computer is not as helpful, although it can help give you ideas. Okay? So if you feel like watching this video, you can on using math or using computers for math instruction. I agree with parts of it, but not all of it. But that becomes up for debate. That is the end of 2.4.